Hello everyone, Assalamu alaikum. Welcome back for another video in the series of deep learning. Well, a fair warning though, before watching this video, you should have a reasonable knowledge about what gradients and function derivatives are, because these concepts shall be used to train our model. So let's get on with it. For this, we will be using a technique called gradient descent, which is related to computing function derivatives and gradients. So consider the linear regression model here again, where the activation function is just the identity function. So this is just like a regular linear regression model. And we have one output here. So this is our prediction. And for fitting or finding these weights, we want to minimize the loss or the prediction error of linear regression. For this, we formulate a convex loss function. In case of least squares, linear regression, that's the sum squared error. We can also consider the mean squared error, doesn't really matter. So either one would work. So for this squared error loss, what we have is we have the prediction minus the actual value that we want to predict. So we consider the difference between the two squared. So y squared, in this way, your outliers will be more heavily penalized, and also it doesn't matter whether one or the others is on the left hand side or the right hand side. Also, you should know that this is over training examples. So if we have a data set with n training examples, this would go from the first to the last training example. So the loss is on the training data set. Now, I plotted the loss here at the bottom as a function of one of the weights. So you notice there are usually multiple weights. Here we are looking only at one of the weights because it's simpler to look at. But you can also generalize this concept to multiple dimensions. So what you can see is this bowl shape or parabola shape, and the loss is minimum for a certain value of weights. So if the value of weights is too large, you can see the loss goes up. Like if we go to the right, if the weight is larger, you can see it is higher loss. In the same way, for this weight here to the left, that loss is too small. So there is a so-called global minimum that we want to find. So we want to find this global minimum for the weights so that our prediction error or loss will be minimized. We will do that for, of course, all the weights. So if you think of this in three dimensions, if we have this W1 and second weight, this would be like a bowl or like a cereal bowl or something like that, where you want to reach the bottom of the cereal bowl. And yeah, it is easier to think of it as maybe it was in one dimension. Let's now see what happens if we use the concept of gradient descent. So what we do is we have to start with a certain weight. Let's say this weight. This is our starting point. So in practice for linear regression, we usually initialize the weights to all zeros or small random numbers. So if I had initialized the weights with value 0, we would be quite up there. And you can also see that the loss would be pretty large here at 0. We want to find basically this global minimum. That's our goal. So if you think about the derivatives, so this is almost like the squared function, so x squared, right? So we can compute derivatives of this function. So the derivative of this function with respect to w1, for example, if we consider our starting weight, so this is the weight we currently consider or we start with. Let's say this is small random number. We can compute the function derivative at this point. So I should say actually the derivative should point upwards here in this direction, but this arrow here is the negative, like negative slope. And we can use this negative slope in multiple dimensions. You can think of it as a gradient instead of derivative. We can use this function gradient to guide the weights into the direction of global minimum. So the slope would tell us how steep the function is, and at a given point how steep this function is, but we are interested in the negative slope, which is also giving us the steepness of the function. But instead of pointing upwards, it's pointing downwards. It's pointing towards the minimum that we want to reach. So we can use this value, this negative slope or negative gradient, to guide the function downwards towards this global minimum. So we make small steps towards the global minimum, one step at a time. And for that, we have, as we have discussed before in a previous video, we had a so-called learning rate, eta. And so the learning rate, eta, together with how steep it is, guides how much we update. So you can see here at the bottom, it becomes a bit flatter, right? So the function is not as steep anymore. So in these cases, we also make smaller steps because the update really depends on steepness and also on the learning rate. So the learning rate is usually a constant that scales all of these slopes. This is like an optional step. You don't have to use learning rate, but in practice, in deep learning, it's kind of required to have a learning rate. And also there will be extensive tuning into what is a good learning rate. So this is something where you would have to try different learning rates and see what performs better. But this is something that will be done later. Now let's try to understand what happens if you have specific learning rates. So if you have a learning rate that is too large, what might happen is that you might overshoot. Like you can see in this animation, if you choose a learning rate that is very large, you may make an update. Let's say you make an update here. So you move from this weight position to this one, and then the next update is large update here. So in this case, the update has been too large. So you are overshooting the global minimum, and depending on what you find here, you may overshoot even more, and then you kind of lose the way. So your loss will increase. You can see that happening in practice also. If you use a learning rate, it is too large. So notice here also, I'm only again always looking at one weight, but there are weights in multiple dimensions. So in that way, there's a lot of possibilities. Something like that can happen if we use a large learning rate. So it's actually better to make it like smaller, small baby steps towards reaching this global minimum, like shown here and here with the learning rates zero point 0.1 and 0.95. Also remember that these are not fixed values for your data set. You might have to go for another learning rate, for example, as this is a hyperparameter. So you might have to play around with it to get the desired value for your data set. Now, if we make the learning rate too small, it will just take a very long time until we reach at this bottom. So we make all these little baby steps that will take a lot of iterations or a lot of updates to reach this global minimum. In practice, for a convex loss function like this one, where we have a global minimum that is easy to reach because everything is convex, then it's not a problem usually to have a small learning rate. We have to just be patient. In practice, for deep learning, this would be a problem because the algorithm can get stuck. So in deep learning, we usually have loss functions that are not convex. Let me show you an example animation of that scenario. So you can see we can have a loss function that is somewhat, let's say, like this. So if we start here, we make small steps, then we may end up in this pit here. This is the local minimum, and then you get stuck here. Whereas the global minimum is here, and because the learning rate is not large enough at this point here to jump over this, for example. So in this case of having a too small learning rate can also be a little bit bad. But in practice, we will talk later about algorithms that have a so-called momentum term and yet to overcome these little challenges also. Now moving on, now you have the overview of the online mode again, just for reference, to just show you what we want to get at now. So what we want to do is we want to find this global minimum. So just pay attention to the right hand side here. This is stochastic gradient descent. There's also a batch gradient descent. I will say a few words about that also. But here, for simplicity, consider the case where we want to update one training point at a time. So in this case, what we do is we compute the gradient of the loss function here. So you can see we compute these gradients, and we have this for W and the bias, and in that case, it would be just partial derivative, not a gradient. But let's use the same symbol, the nebula, for everything. It's, I think, simpler to compute or compare to switching between the symbols. So then our update is based on the current weight, and then the learning rate times the negative gradient. You can see there's a negative now, the negative sign. So this is because we want to go towards the global minimum and not upwards. So we don't want to make the loss larger. We want to make the loss smaller. So we take a step into the direction of negative gradient. So here we actually use these gradients to update. So what are these values? Where does these gradients come from? For that, we can yet drive our loss function with respect to W and with respect to B. Let's now drive the loss function with respect to W. So here we are only taking a look at one of the weights on Wj. Just to keep it simpler, we could also do this for weight vector, but recall the gradient of the loss would be just a collection of these individual partial derivatives. So we would have the partial derivative of the loss with respect to W1, W2, W up to Wm. So that would be a vector. So here we are only taking a look at one of these. For example, the first one, let's call it Wj, some of the arbitrary entries here in this gradient vector. So we are considering here the sum squared error loss. So in the previous slide, I showed you for simplicity on the stochastic version, where we only update or compute the gradient based on one training example at a time, which would be an approximation of this overall loss function. So if I only consider one data point without the sum, if I ignore the sum, this one would be only an approximation of the overall loss function on the training set. So here, using the whole training set, it's actually more accurate. This is also sometimes called just gradient descent or batch gradient descent. If we use the whole training set where we have I equals 1 up to n. And then we can also consider a smaller case where we only have a mini batch. So if we have a mini batch, if this is, let's say, a mini batch of size k and k is smaller than n, this would be the mini batch version. This goes back to what I explained in a previous video, where we have this online mode, mini batch mode, and batch mode. How we compute the gradient, it's the same concept, except that here we have this sum everywhere, but you can also ignore the sum, and then it would be for the online mode. So we are driving now the loss function with respect to the weight. Let's take a look at here. This is just a sum squared error loss. Now we are differentiating this loss with respect to Wj. So in the first step, I'm expanding this term here, the prediction. So if you recall how we compute the prediction, it's the weights times the feature values plus the bias. So here I'm ignoring the bias. Let's say it's implicitly included in the weights. So we are only looking at everything without the bias just for simplicity. I've actually included it here, but maybe ignore this for now. And then we have the activation function, and the activation function was just an identity function. So I'm just using this one here, writing it more compactly with using vector notation W transpose X using um, this vector notation here. So that's what I have here. So I just expanded this one, and now we are using the chain rule to compute the derivative. So the chain rule is the outer derivative times the inner derivative. Here, notice we also have the outer function. This would be this one basic. So this is the inner, and then the squared here would be the outer function. So what I'm doing is I'm driving now the outer one. This is this part here. This is the outer derivative using the power rule. And then on the left hand side here, that's the inner derivative for the outer derivative. We are basically done. So we don't have to do anything on the left hand side. So the left hand side is done. Now let's take a look at the inner derivative. So if we take a look at this inner derivative, we see there is another chain rule application required, right? Because again, we have different things going on here. We have the activation function, and then there is the value inside the activation function. So let's now consider the chain rule again. When we compute the outer and inner derivatives, so the way I have written it here is again on the left hand side, the outer derivative, the derivative of this activation function with respect to its input. So the input is this term W transpose X. And then on the right hand side, I have the derivative of inner part. Notice we cancel the minus y because this is just a constant. So this goes away. All right, so looking at this here, now this term, what if we compute the derivative of this whole term with respect to W, the result would be X, right? Because we computed the derivative with respect to Wj. So this term with respect to Wj, because W is a vector, would be Xj, because all the other values in that vector would be constant. So that is what we have here. That's what we have left over if we drive this part. Now we are left still with the outer derivative to do. So the outer derivative, if we compute that derivative of sigma with respect to its input, it is 1. So why is that? Because we have identity function here. So the derivative of this function would be 1, right? So this goes away. So what we are left here is just xj. So the derivative of loss function with respect to the weights is y hat, and in each iteration, when we do the update or the training, we can compute this value and update the weight values, right? So we can use this term now to update the weight. So if we have the weight, we update it by itself plus the learning rate times the negative version of this whole part. This would be how we update the weights in each round to minimize the loss function. And here I have an alternative notation of this whole thing. This is actually what people do in practice. So usually to make this a little bit more stable within terms of the learning rate, so that the learning rate doesn't depend on the size of the training set. We actually compute or use the mean squared error. So here we have now 1 over n. So just averaging the rest is all the same, except that I have this 1 over n. But also notice that it's only 1 over n, it's over not only 1 over n, it's over 2n. But and again, this is really to make things more convenient, because then we use the power rule. So if I use the power rule here, the 2 goes in front, right? So I have the 2 over 2n, and then the 2 cancel, and then I'm just left with 1 over n. And this is a little bit more convenient. So this one is usually the one that is used in practice, because then if I use this one for updating the weights, I can choose a learning rate that is independent of the size of the training set or independent of the size of mini badges. Otherwise, if I change my data set or my mini badge size, I have to find learning rate every time from scratch again. Actually, it's important to find the learning rate for each new dataset anyways, but if we play around with different mini batch sizes, it would be more robust if we use the 1 over n. This is usually what we do in practice. And here's again how gradient descent looks using a surface plot. So here we have again the mean squared error loss, and we are looking at two weights now, and the global minimum is here in the center. Now suppose we start with the weight here. Let's say this is our starting weight, and the lines here, these contours indicate how large the loss is. So of course the other closer um, so of course the closer you get to the local minimum, the smaller the loss, and that's where we want to get at. We want to get at the global minimum. Now if we use the batch gradient descent, where we drive the loss function based on the whole training set, if we compute the derivative of this one with respect to the whole considering the whole data set, then we make direct leaps towards global minimum. So each update will be perpendicular here to the contour lines. If we use something like stochastic gradient descent, if so that is if we only update based on one data point at a time or based on mini batches, then the update will be a little bit noisier. So instead of going straight to the center, they will be like this zigzagging. For linear regression, this is probably not ideal, because it's why would we want to do that? It's like there's no point doing that. If we can do these direct steps, make these direct steps, why would we do one step at a time? Maybe one advantage is if you have a very large data set, and this will train the linear regression model quicker, because you will be having more updates per epoch. So if you have batch gradient descent, you only have one update per training epoch, and with mini batch gradient descent, you have more updates per epoch. However, each update itself is noisier. Again, for linear regression, it probably doesn't make sense to use mini batch gradient descent, but later we will talk about deep learning. We have non-convex loss functions, so we probably won't be reaching the global minimum anyways. And in this way, using these little stochastic gradient descent updates, I say, are actually better than these complete gradient updates. Alright, so this was all about gradient descent algorithm. If you have any questions, feel free to drop a comment below, and see you in the next video.